So you've heard a bit about the nice overview that Peter gave before, and then you've heard about some applications. Now Peter's going to sort of talk a bit about some more specifics.
Yeah, sure. So some of this is very general, then it gets more specific as the talk goes on. So you can see the title was deliberately slightly provocative, and it's really following on from this theme I finished the first talk with, that I think has been too compartmentalized, and we want to try to bring of that in that it's far more useful than in its original setting of geo, meaning mining and related techniques. And so I'm really just trying to continue that theme of bringing everything into a kind of single framework. So a little bit of history, which in fact Neil has already given a version of in the general introduction, but the traditional definition of geostatistics would be that it was really a very self-contained methodology developed at École des Mines Fontainebleau by, there is the great Georges Matterhorn, the great late Georges Matterhorn, who certainly made it a very successful, but I say essentially self-contained approach to all the problems of spatial prediction, primarily but not exclusively in mineral exploitation. And it took a surprisingly long time for that work to be both known and built upon in the mainstream statistical literature. And I mean, I could speculate on the reasons, but ultimately the first paper I've found that actually says, you know, geostatistics links into mainstream statistics and stochastic processes, and this is how it does it, was by a paper by Jeff Watson, again the late Jeff Watson, statistician, Australian statistician who spent most of his later career at Princeton University, and he wrote a couple of very nice papers making the link between the language and the terminology and the methodology of l'École des Mines and the language and terminology and methodology of mainstream statistics. However, he published it in a geology journal. So he was basically telling the geologists that there was this world of statistics that did similar things than he did, but the statisticians of course didn't read that either. And I think the first person who really brought the connection explicitly into mainstream statistics was Brian Ripley in his 1981 book. The problem with that is that Brian writes in a very terse style, so he basically covered the whole of geostatistics in a 5-page chapter, which wasn't terribly helpful. So I think Cressy's book then really cemented it, and nowadays, you know, everybody accepts that you know, this is part of what we all do. It's very definitely in the mainstream. Now, rather arrogantly, myself and two colleagues introduced the term model-based geostatistics in a paper in 1998, which was really just an attempt to have a pithy title for what was really just saying, we weren't the first to say it, but I think it was the first to systematize it, that geostatistics is really about classes of scientific problem, which you could very briefly summarize as spatial prediction, and there seemed to us no reason why you shouldn't apply general principles of statistical modelling inference to those problems. And what we meant by that was that you just do the classical thing in statistics. You formulate a model, you use likelihood-based methods of inference because we know that the likelihood is the thing, and we use that to answer the scientific question. So that was what we sort of advocated in that 1998 paper. And this is the sort of classical textbook view of what a geostatistical data set looks like. This is a study of lead pollution in Galicia, northwestern Spain, and you can see that it's roughly a lattice design in the geometrical sense, that they wanted to cover Galicia with a regularly spaced grid of sample points at which they measured lead pollution. They deviated from the lattice, I think, just for practical grounds. The way they measured the lead pollution was by taking samples of moss from trees, and I guess in conurbations there ain't enough trees. But clearly the intent there is to see the grayscale as a kind of a rough map of how pollution varies over Galicia, and to refine that by applying some kind of modelling methodology. And the way I would formulate it in the language of Diggle, and Thorne is that we start with a simple Gaussian model for the underlying surface S, and we postulate that the Y's, the measured pollutions, are themselves Gaussian with means, conditional means S of X, and variance tau squared, which is the measurement error in the pollution device. And the objective is to predict the underlying surface S of X. Okay. Now, point processes, which were always considered as really a very different thing from geostatistical models and processes, are just as I've already said in the first half, stochastic models for arrangements of points in space and or time. And that means that what you're looking at when you analyse point process data is trying to understand why the points are where they are. And there's a fairly important distinction between whether you're interested in where they are absolutely or where they are relative to each other. And the distinction there is in the types of scientific question you're trying to address. So there's two examples in which, in a purely abstract sense, each of those examples is simply a set of points xi, ti, I equals 1 to n, defining a spatio-temporal point process. So what I'm showing you there is the spatial margin of a point process that actually exists in space-time. So every dot in each map has a time attached to it. But to me, it's a mistake to think that it would be appropriate to analyse those two data sets using the same models and methods. And the reason I say that is to do with the underlying science. So here we have, you've already seen a static version of this. Here we have Hampshire, and here we have a snapshot from the Aegis project I looked at earlier, with apparently a possible hotspot in the east of the county. This cable, that's clever. You can have the mouse out or the keyboard out, but not both. Right.
It's a resource allocation.
Absolutely, yes. How many meters of cable does this department warrant? But if you actually run this, what you get is a bit of a headache, actually. I'll guess the speed. It's maybe too fast or too slow. There it going. Yeah, well, you get a bit of a headache, as I say. So it doesn't look very interesting, basically, because what you're seeing is that, generally speaking, where there's a lot of people living, you get a lot of dots, and where there aren't many people living, you don't get many dots. But if you actually analyse that statistically, as I did in the previous talk, there is spatio-temporal correlation structure there of a medically very plausible nature, namely it extends over a few kilometres in distance and a few days in time. And that's compatible with it being an acute illness, which arises primarily because people have eaten a contaminated food source, either from a particular shop or a particular restaurant or at home, whatever. So the structure there, but it's subtle, and more to the point, whenever you look through that video, most of the points were in Southampton or Portsmouth, and not many of them were in little villages in the New Forest. Now if you contrast that with the second data set, this is the foot and mouth epidemic that devastated the Cumbrian farming industry in 2001, and the green dots are just farms that at the beginning of the epidemic were holding cattle and or sheep, and you can see that, roughly speaking, they're everywhere except on the high fells. Those of you who know the part of the country will know that what you've got in the middle there are the fells that people live walking on. But wherever it's possible to graze sheep or cattle in the Lake District, people do it. Okay, and so that's the nice pristine foot and mouth free picture of Cumbria. And if we actually started, it actually started in the north and it spread out because it's an infectious disease. And what happens is that when one farm gets infected, it transmits the infection on the air with infected droplets to a neighbouring farm. Occasionally weird things happen, like suddenly you get an epidemic miles away from another one, which is probably due to human indirect transmission on clothing or vehicles or whatever. But the point here is that there's nothing intrinsically high risk about foot and mouth in the north of Cumbria. It just happened to start there, and given that it started there, it spread out. If all I showed you was the final pattern of the epidemic, and I asked you to say, could you identify some environmental risk factors that predispose farms to foot and mouth, you'd look for something that was a lot of in the north and not much of in the south, and it'd be completely wrong, because it's not an environmentally driven disease, it's an infectious transmission disease. Whereas the first one, you know, it might well be that Southampton is a bad place to live for foodborne disease because of generally low standards of hygiene in local supermarkets. I don't know. But the point is although they're both just dots in space-time, it would be completely wrong to think of them as just two equivalent data sets to shove through the same sausage machine. Do I want to close all the tabs or the current tabs?
No, you can close them all.
Thank you. Such gracious people in Sheffield. It's really, yeah. Okay, that's kind of perhaps making a big deal of a small point, but I think it's important to know why you're analysing the data, and don't say, good, XT, I can fit that into my algorithm. So the kind of models I'm talking about for the rest of the talk are very much to do with data like the foodborne disease data rather than data like the foot and mouth data. There's a different talk about the foot and mouth data, which is a completely different statistical approach. And you start with the notion of a Poisson process, and the Poisson process says essentially all that matters is the mean. There's a function. I'm doing it purely in space now. Obviously in reality it's space-time, but for the purposes of the lecture it's easier not to complicate the notation. That says you are likely to get lots of events here and not so many there. And mathematically that's very simple, because if you then look at a map of the realization of that process, it's essentially just an independent random sample from a density function. So very simple to analyze, very tractable for inferential purposes, and the only limitation is your imagination in constructing models for this function lambda of x, and that's all you've got. Any non-negative integrable function will do. A Cox process is a beautiful piece of lateral thinking by Sir David Cox back in 1955, would you believe, who basically said maybe this thing is itself stochastic, and it's this notion of it being because there's something unobserved, something we haven't measured because we didn't know that we needed to measure it, which is actually generating the intensity function of the point process. And that has, obviously, it was invented in 1955 and we're still talking about it, it proved to be a very, very durable and useful idea. And I've borrowed a term from Cressy's book and used this rather horrible phrase, Transgas-Ian, because the idea here is that if you want to build a model for that lambda of x process, you've got to make sure it's non-negative, so it can't be a Gaussian process. But it could be a transformation of a Gaussian process. And frankly, given that we do all our inference by Monte Carlo methods these days, it doesn't matter what the transformation is. So the Log-Gaussian is embedded in the literature because it was what Muller and colleagues suggested you do in 1998. But actually, it has certain properties that in some senses might be unrealistic, basically because the exponential of S of x is such a severe transformation. So if you want to actually use a milder transformation to something non-negative, you should feel free to do it. But the Log-Gaussian one is the one that's most popular, and it does have certain advantages because of its analytic tractability. But if you're doing your inference by Monte Carlo, it really doesn't matter which transformation you use. And to me, this is the epitome of what I call empirical spatial statistics, in the sense there's no presumption of any mechanism in a Gaussian process. It just is. And it's flexible in an empirical way to predict how things vary in space and or time. What it doesn't embody is any notion of mechanism. Now, in what sense could you say, well, this is really just geostatistics by another name? Well, you may already think that's obvious, but just in case it isn't, if you actually couldn't be bothered mapping the points individually, you might settle for counts in regions. And you might then say, the natural model for small counts is a Poisson distribution, and it wouldn't be too naughty of me to simply pretend that these counts were at the centre of each square. So there you are, you've got a geostatistical data set now with Poisson counts. And of course, you're throwing information away there, but as long as your computer's big enough, you don't have to. And in fact, this isn't just a picture, because you can prove mathematically that if you take a Markov random field, right, with Poisson counts, and then take the limit as the grid on which it's defined goes to 0, you do indeed get a point process. You have to make sure, as I said earlier in the Markov random field context, that the thing you start with is a mathematically legitimate Markov random field, and not just any old distribution with Poisson margins. But modulo that's the link. And so you can think of point processes really as just geostatistical data taken to the limit, where you're observing the points everywhere, okay, and they're all yes, no. You're simply observing a 1 where you've got an event and a 0 where you haven't. And actually that's how a lot of the algorithms work. They approximate continuous space by a fine grid of yes, no's, of binary observations telling you where the points are. So, despite the provocative title, the proposal is really extremely mild, which is that we used to call geostatistics this thing on the left-hand side, in which we had an unobserved stochastic process S. We pre-specified some locations, we measured something at each location, and then we used Bayes' theorem to do prediction. And the new definition is really almost identical. It says we start with an unobserved real-value stochastic process, we have some data D, and we are indifferent about the format of the data. That's the key. But we then need to use our model again with Bayes' theorem, to predict S. So it's shifting the focus from the format of the data, which is how most descriptions of geostatistics start. They start by saying, we have got a data set in which we have taken some measurements at locations X and we're interested in an underlying S of X. And it shifts it from the problems, which is that we would like to understand a latent spatial process S of X, and we'll use whatever data we need to understand it. So that's my definition of a geostatistical problem as opposed to a geostatistical data set. Okay, and if your data are points, then the Log-Gaussian Cox process is essentially the version of the standard linear Gaussian geostatistical model. It doesn't have to be correct, but it's the obvious place to start, so that you have your latent Gaussian process, your data and your parameters, and my colleague Ben Taylor, who's much better at maths than I am, has developed a suite of R functions which are now embedded in the second version of a package, LGCP, which has just been accepted for publication, so we should be able to dump it on CRAN fairly soon, which basically then turns the Bayesian handle, but including the Bayesian prior specification. I mean, that's optional, because if you want to be non-Bayesian and just use the Bayes theorem for prediction, what you do is you estimate the parameters offline and then give them very tight priors and work through the algorithm. And the reason I make that point is that very often in my experience for the kind of problems I deal with, the parameter uncertainty in just plugging in theta hat and pretending it's the truth is tiny compared to the very considerable prediction uncertainty because of the sparseness of the data. So if it's a lot of trouble to be Bayesian in the sense of really agonizing over the priors, I think in a lot of prediction problems you don't need to, it's a waste of time. But certainly if the parameter variation matters, then Bayes is the right thing to do to make your predictive inferences correct, allowing for the fact you do not know the model parameters. Okay, so that's all algebra which, if I'm honest, I don't completely understand, and anyway it's all written up. If anyone's really interested, we can send them the LGCP2 paper. Okay, so that's really what it's about, and all I want to do now is just take you through these 4 examples. In fact, I may not even bother with the last one because you've already seen it in a brief form. Mild apologies for the first 3 being purely spatial, but the essence of the problem really is the same within the Cox process environment. I'll say a little bit at the end about that, but within the Cox process environment, space-time is really just an extra dimension to space, and that isn't always a sensible way to think about it, of course. So all these examples really show is that problems which in the past people including me have solved with particular technologies and methodologies that seem okay, you can think of them all as just applications of Log-Gaussian Cox processes. So this is just a map of a forest somewhere in Michigan state. Is Michigan a state? Yes, it is. Yeah. Chicago, that's a city, isn't it? Yeah. And this data set has appeared in several papers and textbooks as an example of non-parametric density estimation. So, people have used various smoothing methods to produce pretty contour maps of the local density of trees in this woods. And the one limitation of them, which I hinted at earlier in answering Nick's question, is that they all give you nice maps, but their inferential standing isn't always terribly clear. And so if you're going to do it as an LGCP problem, then you've got a basis for actually quantifying your uncertainty in your inference about your smoothed map. So lambda of x is the exponential of a Gaussian process. We specify that in a way that fits the data. In this case, I'm using an exponential correlation function, and we produce maps. And that has 2 advantages over the most non-parametric smoothing methods. One is that you can look honestly at how useful the data are. They're very good at telling you about the mean and the variance. They're not actually so good about telling you about the correlation function, and that's why I wouldn't want to over-elaborate the correlation model, because actually I don't have a lot of information in the data about the shape of the correlation function. So those are basically prior versus posterior at the top. Prior in red and posterior samples in black. But the thing that I'm more interested in is the fact that I can get a map of intensity which, unsurprisingly, has nice pale colours where there are a lot of black dots and dark blue colours where there weren't. But it also has these predictive maps, so you can basically say where are we, reasonably sure that there's a low intensity, and where are we reasonably sure that there's a high intensity. Not terribly exciting if all you've got is a map of trees in Lansing Woods, but again an illustration of how, with the stochastic modelling framework, you can naturally produce probabilistic maps which you can tailor to the particular questions that the owner of the data wanted answering. And indeed, what I would want to see in the next version of LGCP is dynamic versions of these maps, where you basically have a slider on what your threshold is, and you can see how the different bits of the map are stable or unstable as you move that threshold. Okay, that's Lancing Woods. Now, this is a problem that still generates controversy, in the sense that it's about bovine tuberculosis in Cornwall, and it's showing you that if you look at the genotypic composition of detected cases of TB in dairy herds in Cornwall, they're very strongly spatially segregated. And that's interesting because it relates indirectly to the ongoing controversy of whether it's the badger's fault or whether it's the farmer's fault. Roughly the idea behind this was that because cattle are bought and sold many times in their life, if primarily they were getting TB by breathing in each other's infected breath at markets, that spatial segregation would erode over time. Whereas if they're being infected from some local source, which may or may not be badgers, then the segregation would be maintained over time. And of course that doesn't establish a causal link. The latter pattern does not establish a causal direction. It may be the cows are infecting the badgers, for example, so we should kill all the cows, not all the badgers. But anyway, it's again an obvious candidate in my mind for a Cox process. This is now a multivariate Cox process, and because testing is done annually, you could, if you wished, although it's not true for this particular map, you can apply the same methodology where these represent the years in which the disease was diagnosed. It is in fact spreading rapidly, this disease, has been for many years. But testing is only annual, so unlike the foot and mouth data, you don't have a detailed spatio-temporal dynamic that you can model. But anyway, this is purely genetic variation, and so you say there's some common element S0 of X, which is an underlying prevalence, if you like, of BTB, and there's an SK of X, which is gene-specific. And if you're interested in understanding all of that, you've got a problem, because from the data I've given you, S0 of X is not identifiable. It would be identifiable if you had a map of all the farms, like I had in Cumbria, but I don't have access to that. It clearly must exist somewhere. But absent that map, what I can identify is the relative intensities of the different genotypes. Okay? So in other words, I can estimate these individual components, but not the overall. And if I do that, I can get these maps of estimated type-specific probability surfaces, rather pompously called. So these are just smoothed out versions of the empirical picture, where you get these very strong local concentrations of particular genotypes with some overlap, but not an awful lot. And if you actually map those, I haven't got the slides with me today, but if you map those over time, that segregation is pretty static in time, which suggests that there's infection and reinfection going on locally rather than at markets. But as I say, that doesn't establish a causal direction. And again, because it's a probabilistic map, you can say, what would you, Mr. Defra, describe as an area where a particular genotype was dominant? So if you would say it's dominant if at least 60% of the cases are of type 1, then these are the dominant areas of the 4 genotypes. If you have a more stringent definition, oh sorry, I'm confusing two things, right? If your definition of dominance is that at least 80% of the local cases are of that particular genotype. Well, if you're prepared to take a punt on being right, 60% chance, then you've got these areas. If you operate a more stringent criterion, saying no, I really want to be 90% certain, then essentially there are no areas where these two are dominant, just odd little spots. And you can see this much smaller area where we're more or less certain, i.e. 90% certain, that we've got dominance of one genotype in the east and another genotype more in the central area. No, I was about to say something, then I remembered I was being recorded.
That's the problem with recording.
Yeah, that's right. Something about DEFRA, but never mind. Now, this is something I mentioned earlier, but we're now actually doing it, and you can judge for yourself whether it's worth the effort. This is a page from the Spanish Cancer Atlas, beautiful, like all these atlases, a beautiful glossy volume with many, many maps that look like this. And it's based on fitting the Bizag-York-Mollier model, Markov random field model, to these small areas, and this in a particular part of Spain. And you can see the variation going from, in relative terms, going from about 2/3 of the national average up to 1.5. in cancer incidence rates. And using the LGCP, we said, no, what you actually got is a continuous process lambda of x, in which d of x is basically what a statistician calls an offset. It's the population density. So if nothing interesting is happening, you'd expect incidence to be proportional to population density, but that can be moderated by covariates to do with, for example, age-sex distributions or socioeconomic indices, which in Britain at least, and probably in Spain, are remarkably good predictors of all sorts of diseases, plus the bit you don't yet understand and you want to see if there's any there. And really, as a public health professional, you'd like S of x to vanish, because if you can identify all the Z of x's that matter, you can decide which ones you can do something about. If they're all about poverty, you know what to do. If they're all about quality of air environment, you know what to do. If they're S of x, you don't know what to do, you just know there's a lot of it here and not much there. Ooh, sorry. So we get this predicted risk surface, and unfortunately we haven't done a good job we haven't even attempted, I'm afraid, to match the colour palette, so you can't directly compare the colours. But the only real point about it is, well, there are 2 points about it. First, that there is variation within the small areas, basically because this d of x and this z of x are more finely resolved than the outcome. And secondly, again, the general point, flogging it a bit, I realise, is that you can actually say it's not so much what the point estimate is that matters, it's whether we've actually got an area that's materially higher than it should be, in the sense of being materially worse than we would predict for known causes. And that's where we might want to actually focus public health efforts in bringing it back into line with the rest of the region.
Just be an understanding question,
Yeah.
Peter. So the resolution at the state, so you've got outcome at the state level.
Yeah, outcome at these black polygons, right? But we've got covariates at a finer level.
So how are you, when you make the prediction for a given outcome, how do you assimilate the covariates? Are you integrating across the region?
Yeah, exactly. I mean, the likelihood involves integrating these over areas, but then with the predictions, you can then predict at the finer scale. So in terms of estimating the parameters, essentially, you've got to have the likelihood which is at the large area scale. But then, if when you predict, you recognise that within each of those areas these things are varying, then what you've estimated about beta will tell you how to vary the local risk within each area.
Is that something you're using Monte Carlo for? Yeah.
That's another MCMC. I'm not sure whether we can do that in the version of the LGCP package that's about to be put on CRAN. I think we can. We can certainly do it in-house. I think it's in the package that's about to be released as well. Clearly, a dyed-in-the-wool data analyst would say, you're kidding yourself, because clearly if your data on incidence or area level, anything at sub-area level has to be model-driven. But I guess, as those who know me well will know, I kind of think if you aren't prepared to make some assumptions over and above the data, you might as well not bother, because you don't need a statistician. So, but the art of balancing, it's a bit like I said about soft data, those extra assumptions buy you information. Is it a good buy, or have you actually put in some spurious precision that's not justified? And that's a fair question of any model-based analysis. Okay, but in principle, it's echoing the point I made about the leptospirosis, that the process is spatially continuous. And so ideally, your model should recognise that. And if there is also spatially continuous information available, then potentially that buys you some extra information that might be useful. Whether it does or doesn't in a particular application is a moot point. Okay, so I'll skip the AGIS example because we've already seen it. I'll just finish off with what do we do with spatio-temporal models. And what we often do is something very naive, which is called separable structure, which is you say the space-time correlation function is just a product of a purely spatial correlation function and a purely temporal correlation function. Hard to think of any physical justification for that, but empirically it often doesn't do a bad job. And it's again because, depending on how much data you've got, of course, prediction problems are hard, and therefore pretty crude models are about all that you can well identify from the data. So although in principle you could do better with a better model, if you're actually having to estimate parameters in that, quote, better model, often it doesn't buy you much predictive accuracy. But there is some literature on extending this idea by introducing a term that builds in non-separability, and there are 2 or 3 suggestions in particular, any of which I'd be happy to follow up with people by email if they're interested. I think maybe I've not, I can't remember whether I've included a reference. There's a nice review paper by Tillman and Knighting, which I can send people the reference to if it's not at the end of the slides. But you could also, even slightly contradicting what I said earlier, even within the Log-Gaussian framework, you could try to put some kind of mechanistic behavior onto the Gaussian process. So this is a kind of a saying that the reason why the process evolves over time is because we're basically smoothing, right? So that what's happening here and now is basically some spatial average of what was happening some time ago, plus some random introduction, and you want to define a model in which that thing has a sensible physical limit as delta goes to 0, because delta is the time step, and to get a spatio-temporally continuous model you need that time step to go down to 0. So there's an example of this in a JRSSB paper going back about 10 years, and the authors, Gareth Roberts and colleagues, call it blur-generated spatio-temporal Gaussian processes. So if you're thinking of something, basically about what happens now is assimilating what's been happening recently in some area, there's a kind of semi-mechanistic connotation to that. Now, if I'd had a fourth bullet point, I could have put stochastic differential equations, and some work by Håvard Rue's group in Norway is following that line up really quite productively. And I must say, although I haven't talked explicitly much about spatio-temporal as opposed to spatial in these actual lectures, the great thing about spatio-temporal is it's actually so much easier than spatial, because the idea of conditioning on the past is so powerful that you can do an enormous amount with spatio-temporal data that you can't do with purely spatial data. And so, it's a ripe area for building interesting models that exploit the much richer data sources that we have available now. It's kind of a historical accident that people got interested in spatial data because it was hard, and if we'd had good spatio-temporal data 30 years ago, I think the subject wouldn't have evolved in the same way at all, because it would have developed from time series rather than as a completely new separate thing. Anyway, that's a personal observation. Maybe rubbish. So what's my sort of general view in all of this? This is kind of the conclusion to both lectures, is I like to sort of promote the view that when you're building statistical models, that you should start not with the data but with the problem. And following on from that, most natural phenomena are spatially continuous. So that doesn't mean you have to build a model that's spatially continuous, but it means you have to think about why you're not doing it, rather than just knee-jerk. Discrete data implies discrete model. A lot of what we're talking about just reduces to an application of Bayes' theorem. And again, to be deliberately provocative, that's got nothing to do with being Bayesian, right? It's just to do with believing that maths actually works. To me, modelling an unobserved stochastic process and assigning a prior distribution and an unknown parameter are very different things. They obey the same mathematical calculus, but they're very different things, and you should approach them differently accordingly. And in particular, I think in practice, if only for pragmatic reasons, there's a distinction between modelling when your goal is empirical prediction and modelling when your goal is understanding mechanisms. And I think I've forgotten to add references to this, but in fact this talk is very, very much based on this one paper just published in Statistical Science, so the references are actually at the end of that paper. And so all the technical stuff, Ben Taylor takes responsible for the MC-MC algorithms, Barry Rowlingson does the nice mapping, and Paula Moraga sadly is going to Harvard next month, so won't be able to do much more for us, but doubtless she'll thrive in Harvard. Okay, thanks very much.
Questions?
Okay, so you talked about the temporal dimension at the end. Near the start you said you can kind of treat it the same, but I wonder what about the issues in terms of causality?
Yes, that's why I said partially contradicting myself. If you simply want an empirical... go back to my slide. If you look at the literature around these two bullet points, although they use the words space and time, there isn't really anything dynamically temporal about it. It's basically just saying we want to go from 2 dimensions to 3, and the dimensions are incommensurate. So we can't just treat it as... it would be totally naive to say, oh, it's just 3-dimensional space. But 2 plus 1-dimensional space is okay if you just want to empirically describe what happens. Now, when you get into this third bullet point, that's when I said I was beginning to contradict myself, because there you are very explicitly modelling conditional on the past. And my final comment about space-time being so much easier was slightly tongue-in-cheek. A better word would be it's so much richer, because conditioning on the past and bringing in scientific understanding of causality not only enriches your models, but it also makes the inference easier, because basically any likelihood can be written as a product of conditional distributions, and if those distributions are time ordered, the conditioning is very natural, and it's quite easy to think about how to build models that at least make sense. Whereas if those distributions are purely spatial, then how you label the variables gives you a different answer, and the models just make no sense unless they're invariant to labeling. But in space-time, you absolutely don't care. You positively want them to be not invariant to labeling, because time matters, it has a direction. So I think getting at causality and mechanisms is really the way to go. But if at the end of the day what you're doing is a purely empirical prediction problem, and your data are relatively sparse, it may be that you can think of some fancy mechanisms, but you don't actually do much better than these simple things. You know, horses for courses.
You mentioned that there's this positivity constraint.
Yeah.
To my understanding, that's why you're using the Log-Gaussian.
Yes, exactly. Yeah. Yeah.
Are there any constraint-based approaches, like in constraint truncated Gaussians?
Yeah, I mean that was. I mean, although I've not, I've only experienced doing things which are milder in the sense if you say that your intensity is the square of a Gaussian process, that's less extreme in the sense of a mathematical transformation than an exponential. But that's what I was trying to hint at when I basically wrote the definition down as Transgaussian. Which is that, you know, anything that guarantees non-negativity is legitimate. In practice, when you actually let them be actually equal to zero, that can have a very powerful effect on the inference if you're not careful, because obviously it's implying that the events of probability is zero, and as soon as you find one, your model falls apart, whereas saying they're events of very small probability is kind of a more robust thing to do. But yes, there are situations when you genuinely do want to have contextually informed transformations that really wouldn't even necessarily have a simple analytic form. There's no, again, because the inference is Monte Carlo, there isn't really a problem. All you have to be able to do is unambiguously undo the transformation and believe that a Gaussian process is plausible in that untransformed space. Something I haven't mentioned, but we've come across in a time application recently, is although I've really sort of hammered the idea that what we really want to do is make predictive probability statements, if those predictive probability statements are in the tails, then of course what you should be more worried about than the transformation is the Gaussian assumption. And you know, again, with the tools that are now available to us, we have got the facility to investigate heavy tailedness as one of the things that might make your predictions less than robust if you're interested in predicting extreme behaviour. I haven't got any active experience of going there yet, but we're just beginning to think about the implications in some of our applications where we want to predict, not extreme in the sense of extreme value 100-year floods, but you know, towards the tail of the distribution, the Gaussian assumption becomes critical and the data give you very little direct information on how accurate it is in the tails.
You know, trying to pretend to be a statistician for a moment, I would very, you know, I like this, you can put any F in there. But there's an issue of interpretability when it's non-log for your additive model, isn't there?
Oh, yeah.
In terms of you no longer have that separation, the product of the mean function and the non-parametric.
Yeah, that's kind of what I meant by this bullet point there.
Right.
Yes, if you've got, it's a bit, well, maybe it would be a version of what I said about continuous and discrete space. You absolutely don't have to use the log. On the other hand, I would do other things only when I had a positive reason to. You know, if you just actually draw pictures of these log Gaussian processes, if you're not careful, they can degenerate into sharp spikes and long, empty bits in the middle, which for some applications is just too extreme. But if they fit, then they're nice because of this. And you have to have a positive reason for saying, well, no, they don't fit, and therefore have to think of something else. And the something else is likely to be contextually informed. I kind of think of these as the sort of contextually neutral starting point. Yeah. And you continue to use it unless and until the context says, no, I know about the science here, and the science tells me this is wrong, you should be doing something else instead.
Maybe with respect to the tail correlation issue, copula, for example.
Well, yeah, exactly so. Exactly so, yeah.
Another thought is, have you ever tried applying the nonlinearities to each part of the process separately?
No, but you're right. There's no reason why you should. There's no reason why you shouldn't. I mean, you probably have something more sophisticated in mind than what I do. But
I was just wondering how you can get that analytic tractability out, so you're ensuring somehow the parts may be separable, like their products.
Yeah, exactly so. Yeah, no, I was just thinking. I can't find a slide.
This exponential transformation, so because of its ugliness. But you want to retain, and maybe sort of applying several nonlinearities on each part of the process.
Yeah, absolutely.
Global nonlinearity.
Yeah. So I mean, the neat result you've said that the nice thing about the Log-Gaussian framework is that you write down the regression part plus the stochastic part, and as I made a virtue of earlier, you can see that if you're transferring the stochastic part into the regression part, you're not changing the model, you're just adding information to it, and that's nice. Whereas if you don't have the S of x appearing algebraically in the same way as a covariate, then the interpretation of the model changes when you add covariates. So yeah, you do pay a price for going away from the log linear formulation, but it's not an infinite price, so it's worth thinking about. Yeah.
I guess one sort of final part I had, actually you ended up covering, you said it's difficult to put the interpretability in the covariance function.
Oops.
But then I think you actually showed, this is a formalism we've played with as well.
Yeah.
So where you drive, you have some, this could be the result of a solution of a partial differential equation, a spatio-temporal partial differential equation, and you put information in that differential equation and have some assumptions about what the initial conditions are, which actually would fit quite well with the foot and mouth disease, that it's a diffusion from a point. And that actually leads to the squared exponential type smooth process. It's a Peter equation.
But it depends on the form of H. You see this, because the other thing is in purely, as again I'm sure you all know, I mean it's a different, the details are different, but the principle is the same. If you think of this as a convolution of a set of random variables, then again there's an equivalence between representing a spatial process as a process with a continuous correlation function and a convolution, right, with a kernel, and there's a duality between the kernel and the correlation structure. And in fact, sometimes when we're fitting these models, we actually do low rank approximations of these things for that reason. But mechanistically, as soon as you've got time in there, you feel, I mean, this feels a lot nicer, doesn't it, than just coming up with some mysterious function that Tillman Ganiting wrote down because it obeyed the maths. I mean, that's not criticising Tillman, he's great, but is Nick still here? Because it's absolutely not to criticise Nick either, but when he wrote a horrible equation down, you think, oh, okay, but it does a job. Basically, that was one of these. But if he'd written that down, you'd have said, oh yeah, I see what's going on there. And it helps if you can give a sort of semi-physical interpretation to how your model is structured, because you feel you can have an intelligent debate about it. Otherwise, they're just Greek letters that you estimate.
You can some of this you can extend spatially as well. And I think one possible justification for the separable covariance is certain partial differential equations lead to separable Green's functions. And then you can sort of see what your physical assumption must be in order to have got this separable Green's function. And I think we need to do a lot more of that. We were talking a lot in the winter school about precisely that. You've got this crazy covariance structure, and where on earth did it come from?
Where did it come from? Exactly so.
And very often it's helpful to know how it was derived.
Absolutely. No, I think that's a particularly nice point, Neil, because in a sense, at the end of the day, all that matters for anything Gaussian is its covariance structure, right? But getting the covariance structure from something that has a kind of intuitively attractive feel to it, that means you can actually understand what the various parameters are doing, is actually much nicer than just saying, here's a mysterious function, and I'll just fit the parameters. And I mean, what you've just said there is a more sophisticated version of what I said about why I like the Matern function, is that the parameter that's difficult to estimate has a nice interpretation in terms of differentiability. And this is better still, because although all this really does is generate a correlation function, it's one that stems from a nice physical representation of how something might indeed change over time.
I've been deliberately letting it overrun because I was enjoying that. That's the chairman's privilege.
Of course, the others weren't, but that's their problem, isn't it?
But that does potentially lead to some. We've got 5 minutes for the next. Can we just thank people again?